When it comes to batteries, the first thing that comes to mind is definitely lithium batteries. From the smartphone in your hand, the laptop on your desk, to the Tesla driving on the road, lithium batteries, with their extremely high energy density, have dominated our era for over 30 years. It seems so perfect, appearing to be the ultimate answer for energy transition, even earning its developers a Nobel Prize. But reality is very cruel. The abundance of lithium in the Earth's crust is despairingly scarce, accounting for only about 0.0065%, and it is extremely unevenly distributed, mostly concentrated in the lithium triangle of South America. With the explosive growth in demand for global EVs and energy storage, lithium ore is no longer just a material. It has become a geopolitical shackle. When resources are monopolized, price fluctuations are like a roller coaster, skyrocketing from tens of thousands to hundreds of thousands of RMB per ton. This is enough to instantly wipe out the profits of any major automaker and cause supply chains to collapse at any moment. This is the fatal Achilles heel under the dominance of lithium batteries. What if we could use the salt found everywhere by the sea, which is sodium, to replace the scarce lithium? The abundance of sodium in the Earth's crust is 1,350 times that of lithium, and it is readily available all over the world. Today, we are going to deeply deconstruct the underlying logic of sodium-ion batteries, to see how engineers turn cheap salt into a dimension-reducing strike weapon in the energy market. To understand sodium batteries, we first need to look closely at its predecessor, the lithium battery. The operation of lithium ions is essentially a rocking chair battery, where ions act like tiny porters, shuttling through the lattice gaps of the positive and negative electrodes. Lithium is the third element on the periodic table, with an extremely small atomic mass and extremely high potential. This means it can carry an immense amount of energy with very little weight. However, when we try to replace lithium with sodium, the ironclad laws of physics immediately slap us in the face. Sodium ions are located just below lithium on the periodic table. Its ionic radius is a full 25% larger than that of a lithium ion, and its volume is more than double. Imagine lithium ions as nimble compact cars that can easily squeeze into the layered gaps of the graphite anode. But sodium ions are bulky trucks. In the graphite anode used in traditional lithium batteries, the interlayer spacing is only 0.335 nanometers. The large truck of a sodium ion simply cannot squeeze in. If you forcefully increase the voltage trying to stuff it in, the graphite layers will directly collapse like an overstuffed bookshelf. The battery will quickly short circuit and catch fire. This physical barrier kept sodium batteries locked down for the past 30 years, inside laboratory freezers, considered by mainstream academia to have absolutely no possibility of large-scale commercialization. This is the moment engineers showcase the brutal aesthetics and shift the underlying logic. Since the graphite track is too crowded, and the large trucks can't drive in, then let's tear down the track and rebuild it. Engineers abandoned the neat and regular graphite and switched to a material called hard carbon. Microscopically, hard carbon is not like a neat stack of paper like graphite. It is more like a violently crumpled ball of paper. Under a scanning electron microscope, you can see it is filled with a large amount of distorted microcrystalline structures and huge voids. These chaotic spaces, like illegal constructions, have an interlayer spacing for greater than 0.37 nanometers, which is exactly enough to give the bulky sodium ions plenty of room to enter, exit, and settle. An even more dimension-reducing underlying advantage lies in the current collector material. In lithium batteries, lithium undergoes an alloying reaction with aluminum foil at low potentials, so the negative current collector must use expensive copper foil. But sodium ions are very special. They do not react with aluminum. This means both the positive and negative electrodes of sodium batteries can directly use cheap aluminum foil. The price of copper is 3 times that of aluminum, and its density is more than 3 times higher. This not only drastically reduces material costs by over 30%, but also makes the battery pack lighter with less energy density loss. This is not an incremental improvement. This is a brutal deconstruction of the cost structure starting from material physics. You might ask, since sodium is so cheap, and hard carbon solves the problem, why didn't we just skip lithium in the past and jump straight to the sodium era? Because early sodium batteries were simply an engineering disaster. Even though sodium ions can enter and exit, due to their large volume and heavy weight, the kinetic performance was extremely poor. At low temperatures, the electrolyte becomes viscous, and the giant sodium ions are like beasts crawling through mud. Moreover, the structure of early hard carbon materials was unstable. After dozens of charge and discharge cycles, the internal microcrystalline structure would be shattered by the repeated impact of sodium ions, shattered, and expand, leading to an extremely short battery life. But now, the seal has been broken. We have overcome the nightmare from microscopic materials to macroscopic processing. By precisely controlling the heat treatment temperature of hard carbon, usually between 1000 and 1500 degrees, engineers can accurately adjust the porosity, making the diffusion path for sodium ions within it the shortest. Coupled with modern fully automated production lines, we can coat the electrodes with nanoscale precision. Today's sodium batteries are no longer low-end products. In extreme cold environments of -20 degrees Celsius, they can still maintain over 90% of their capacity output and support fast charging of 4C or above. This stability demonstrated in extreme environments is precisely the manifestation of modern engineering precision control. To truly secure the throne, sodium batteries still have to face their strongest opponent, the structural stability of the positive electrode material. If the negative electrode is the track, the positive electrode is the starting base. In lithium batteries, layered oxides are very stable, but in sodium batteries, when the giant sodium ions extract, the electrostatic repulsion between the positive layers causes the structure to instantly collapse like building blocks. Engineers brought out two ultimate technical routes. The first is layered peroxides. Through multi-element doping such as nickel, manganese, and iron, the crystal lattice is made much more resilient. The second route is the Prussian Blue analogues, which possess a hardcore aesthetic. This is a cubic structure material with an open framework. From a microscopic perspective, it looks like an extremely sturdy steel frame skyscraper, with broad and vertically intersecting internal passages. Even if truck-sized sodium ions violently crash around inside it, the main steel framework of the building remains completely motionless. However, the ultimate boss of the Prussian Blue route is water of crystallization. During the production process, if even a tiny bit of moisture remains in the voids, it will decompose under a high-voltage electric field, producing gas and causing the battery to swell. This requires the production environment to achieve extreme low dew point dryness. This is a pinnacle showdown between materials chemistry and manufacturing processes, and it is also the core secret to why sodium batteries can maintain a cycle life of over 3,000 times. Once we see the underlying logic of sodium batteries clearly, we will understand that it is not meant to completely eliminate lithium batteries. Lithium batteries, especially ternary lithium, are still king. But the rise of sodium batteries is meant to fill that long-forgotten massive market. Large-scale energy storage, low-speed electric vehicles, and the northern markets with rigid demands for low-temperature environments. In the future, we will see highly creative AB battery solutions. In the same battery pack, lithium battery cells and sodium battery cells are mixed and installed, using the high density of lithium batteries to provide range, and using the low-temperature performance and low cost of sodium batteries as support. This heterogeneous integration is exactly the essence of engineering thinking, not pursuing the extreme of a single metric, but pursuing the optimal solution for the overall system. In the world of engineering, every choice is a trade-off. The scarcity of lithium prompted the renaissance of sodium batteries. This is not merely a substitution of chemical elements, but human civilization's collective evolution in an attempt to shake off the geopolitical shackles of resources and use the most abundant element on Earth to achieve energy freedom. Only when we learn to use the most ordinary salt to store energy will we truly open a new era of affordable energy. This is the hardcore engineering logic behind sodium-ion batteries. From the microscopic ionic radius to the macroscopic supply chain wars, we can see that behind the breakthrough of every technology lie countless challenges to physical limits. Do you think this type of salt battery, which is universally available and extremely low cost, can really lower the price of electric vehicles within 5 years to a range where ordinary consumers will no longer hesitate? If you are interested in the hard carbon anode that engineers both love and hate mentioned in the video, and its sintering process, or if you want to see more about the dynamic simulation demonstration of the Prussian Blue structure, please let me know in the comments section. If there are over 500 comments, I will prepare a special episode, taking everyone deep into the laboratory's drying room to see this peak showdown of positive electrode materials concerning fire and water. Lock into the most hardcore tech deconstructions. See you next time.